Energy efficiency in AI.
Okay.
I know what you're thinking.
Yeah.
Not exactly the sexiest topic in the world of cutting-edge AI research.
Right.
But seriously,
Mm-hmm.
this stuff matters,
It does.
especially if you're like us
Yeah.
and you're neck deep in large language models day in and day out.
Absolutely.
We're talking about a paper today
Okay.
that has the potential to be a real game changer.
Okay.
Addition is all you need for energy-efficient language models. That's the title.
Yeah.
And we have a bona fide AI efficiency guru with us today to help us unpack it all.
Happy to be here.
So can we just talk about the elephant in the room for a sec?
Sure.
The energy consumption of these large language models is
Out of control.
kind of insane.
Right. It's definitely a concern.
I mean, we've all seen the headlines.
Yeah.
ChatGPT using as much power as a small city.
Right.
Yeah.
It's getting hard to ignore.
It is. In this paper, it actually put some hard numbers to it.
Oh. Yeah. They say multiplying two 32-bit floating point numbers, FP32, costs 4 times energy as adding 2 FP32 numbers, and 37 times higher cost than adding 2 32-bit integers in 3032.
So for those of us who maybe don't eat, sleep, and breathe floating point operations,
Right.
what's the big takeaway there?
It's a big difference.
Why is AI so energy hungry
Yeah.
in the first place?
So it really comes down to just the sheer number of calculations involved
Okay.
in training and running these models.
Right.
We're talking about billions, trillions of operations.
Yeah.
And a lot of those are these floating point multiplications.
Floating point multiplications.
As
Those
you
are the
say.
really energy-intensive ones.
They are. And the paper does a good job of breaking down just how much more energy we're talking about compared to simply operations like addition.
Okay, so that brings us to LMUL.
Mm-hmm.
This is the heart of the paper.
Okay.
They're basically saying,
Yeah.
what if we could replace those power-hungry multiplications with something simpler?
Yeah, and that's exactly what they're trying to do with this LMUL.
Okay.
They ask, can we approximate FP multiplication with simpler, less energy-hungry integer additions and still get accurate results?
And what do they find?
They seem to think so.
Really?
Cautious.
Okay, so
Yeah.
how does this LMUL thing even work?
So basically, it bypasses the most complex part of floating point multiplication.
Okay.
It uses a combination of these simpler operations, additions, and bit shifts to approximate the result.
Okay, so less complexity,
Right.
less energy,
Mm-hmm.
but does it compromise accuracy?
That's the million-dollar question, right?
Yeah.
And this is where it gets really interesting.
Okay.
They say LMUL with a 4-bit mantissa is on par with or even better than standard 8-bit FP multiplications on various tasks.
Hold on.
Yeah.
Mantissa.
Right.
You're going to have to
Yeah.
explain that one.
So the mantissa is basically the significant digits of a number. So what they're saying is that even with LMUL using a smaller number of significant digits, it can still achieve the same or even better accuracy than standard floating point operations.
So we're talking about matching performance
Potentially.
with way less energy.
Yeah.
That's...
It's a win-win for AI developers.
Yeah.
Absolutely.
So what kind of energy savings are we even talking about here?
So they say that replacing floating point multiplication with integer addition could lead to roughly a 95% energy reduction for element-wise operations.
95%. That's
That's massive.
wild. That's huge. You know,
But let's not get ahead of ourselves.
Right.
How does this LMUL actually perform
Yeah.
in the real world?
Right.
Did they actually test it?
They did.
Okay. They actually tested it.
They did a bunch of experiments.
Okay.
Yeah. They really put it through its paces on a bunch of different benchmarks.
So like what?
So first
Yeah.
they started with language-based tasks.
Okay.
You know, since we are talking about language models.
Makes sense.
One of the big ones was this MMLU benchmark.
Massive multitask language understanding.
Yeah, you got it.
I've heard of that one.
Yeah, it's a really...
Comprehensive test
Yeah.
of how well a model really understands language.
Okay. And how did LMUL do? Yeah.
So get this, in a lot of cases, the
Okay.
models using LMUL were just as good
Okay.
or even better than the regular models using the standard multiplications
On the MMLU.
on the MMLU benchmark.
So same accuracy.
At least
Potentially way less energy consumption.
way less.
That's huge.
It's a big deal.
Okay, so
Right.
MMLU, that's like
Right.
General knowledge.
Yeah, like general knowledge and language understanding.
Did they test it on anything more?
Yeah, they wanted to see
Twice.
how it did on more complex reasoning.
Okay.
Stuff like that.
Gotcha.
So they use this other benchmark called Big Bench Hard, or BBH.
Okay.
And that one is designed to really test these complex reasoning abilities.
So like the kind of problem solving we usually think of with really advanced AI.
Exactly.
Okay.
And this is where it gets a little interesting.
Okay.
The results were a bit more mixed.
Okay. How so?
So on some of those really hard reasoning tasks,
Yeah.
the L-Mule models didn't do quite as well as the standard models.
So there are some limitations.
Yeah. It's not perfect.
It's not a magic bullet
It's not magic.
for every AI problem.
Exactly. But it's important to remember this is still early.
True.
And even with those little hiccups,
Yeah.
we're still talking about potentially saving a ton of energy.
Right. It's always going to be a trade-off, performance versus efficiency.
Yeah.
But if you can get close
Right.
with a fraction of the energy cost, that's a win.
Definitely a win.
Okay, so we talked language,
Right.
but AI these days is more than just language.
It is.
What about images?
They tested that too.
Really?
Yeah.
Okay.
They did a bunch of experiments with visual question answering.
Okay, so like
Yeah.
show the model an image.
Exactly.
Pick questions.
You got it.
Okay.
See if it can understand what's going on. They used a few different benchmarks for this one. VQA V2,
Okay.
VizWiz,
Okay.
Text VQAA.
Okay.
And again, the Elmore models did surprisingly well.
So not really losing accuracy,
It seems like it.
but using way less energy,
Potentially way less.
which is huge
It is.
for things like computer vision,
Especially for computer vision.
which is
Yeah.
becoming more and more,
Ubiquitous.
Yeah.
It's everywhere.
we need to make it more sustainable.
Absolutely.
Okay, so we've talked about using Elmore in these
Yeah.
specific parts of the model,
Right. In the attention mechanism.
but what about training the model in the first place?
Right.
That's
Yeah.
where a lot of that energy consumption actually happens.
Yeah, that's where it gets really interesting. Yeah, that's where it gets really interesting.
Did they actually look at that?
They actually did an experiment with this.
Okay.
They took a model called Gemma 2 to B.
Okay. Fine-tuned it on this data set of math problems called GSM8K,
Okay.
and they replaced all the floating point multiplications with Elmul.
Wow. So like the whole training process?
The whole thing.
Using Elmul.
Elmul all the way down.
That's kind of wild.
It is pretty wild.
Okay, so what happened?
Okay, so the Elmul model
Yeah.
did basically just as well as the regular model.
No way.
Yeah,
So even with this completely different way of doing the math,
totally different.
it still learned
Yeah,
and performed at the same level.
pretty much, yeah.
That's a huge
That's a big deal.
deal for efficiency if that
It is.
holds up.
Absolutely.
Okay, so this all sounds really promising,
It's exciting.
but are there any catches?
There are always catches, right?
Yeah, nothing's perfect
Right.
in the world of AI.
One thing they mentioned is that to really make Elmul shine,
Okay.
you probably need specialized hardware.
Okay, so like
Because you
you can't just run this on
can simulate it.
on like a regular GPU,
Gotcha.
but it's not going to be as efficient.
Right. It's not designed for that.
Exactly. It's like trying to
It's like fitting a square peg in a round hole.
Exactly.
Okay.
And they also pointed out that their error analysis,
Yeah.
it's based on some assumptions
Okay.
about the data that might not always be true in the real world.
So more research is needed
Definitely.
to really know.
Yeah, to see how it generalizes
And all this works.
to other kinds of data,
Okay.
other tasks.
Gotcha.
But you know, it's a good first step.
Yeah.
It's promising.
It's a really interesting
Lots of exciting research.
direction for the future of AI.
For sure.
We've covered so much ground today,
We really have.
from the nitty-gritty of these
Oh,
floating point
exciting.
operations,
Floating point multiplication.
the potential of this Elmul to like
Yeah, it could be.
revolutionize things.
Radically change things.
What's the big takeaway?
I think the big takeaway is that we really need to start thinking differently about AI efficiency.
Okay.
It's not just about making these models bigger and smarter anymore.
It's about making them better
Exactly.
For
everyone.
for everyone,
For the planet.
for the planet.
This has been amazing.
It's been a great discussion.
Thank you so much for joining us today.
Happy to be here.
And to everyone listening, keep pushing those boundaries.
Keep innovating.
Keep asking those tough questions.
Absolutely.
And let's build an AI future that we can all be proud of.
I'm all for that.